Okay, this is a book called Learning LangChain published by O'Reilly, and it's by Mayo Oshin and Nuno Campos. So it should be a good text probably because O'Reilly is a good publisher. So they have here a link for the errata, so the mistakes that are in the book. So here's a little history on this date, this year. Uh, OpenAI publicly released ChatGPT, and it became attracted over 100 million monthly active users. Actually, now I think it's almost a billion, so everyone knows about it now. So we're talking about building LLM applications. So of course, we need an LLM if we're going to call it an LLM application. So we might ask, what do we mean by an LLM application? Because we know what we mean by an LLM, but an application of an LLM is some program, maybe I'm just making this up, but some program that uses the LLM to accomplish some particular task. Programs, of course, try to accomplish various tasks, and if you include the use of an LLM during the process of trying to accomplish some goal, we might call that an LLM application. That's a little bit biased because it's using a lot of things, not just the LLMs. It's using all kinds of programming techniques and so on. But LMs are sort of the new part, so we call it an LLM application, at least for now. So what does it mean to use an LLM in an application? It means like you have something that you need, part of your program needs to do something, and you let the LLM do it instead of sort of programming something to do it. You just let the LLM give an answer instead of programming something to give the answer. So that might be just one part of your program, but you're relying on an LLM to give you some response to something. Maybe it can do all kinds of things, but whatever it does, spits back some information to you, and you use that, then you're using the LLM in your program. So that would be called an LLM application. So they do, at the beginning of this book, they want to introduce the learner to basic concepts of machine learning. And so I think we'll probably skip that. Now, here in this PDF, we don't have I guess, the full access to the full book. So like this is obviously supposed to be a sliding bar here, but it's not. It's just an image. So we have to suffer with that. So they want to discuss what is an LLM. So we all use LLMs, but we might just briefly go through what they say here. Now, if you want to, you can read this more completely. I'm not going to go through the whole text word for word, but they're saying that it's kind of just it's like something that's fairly familiar, which is autocomplete. So when you type in something uh, into like a Google, you start to type a phrase, and it will sort of guess the next word that you want and suggest or give you a bunch of suggestions, and then you can just sort of hit the tab or click on one of them, and so it tends to be faster. So where does it come up with that list of words? So that's kind of like what an LLM does. It's predicting the next word based on the previous words. So I think I won't go through this large language model description, and I will let you read this yourself if you want to. But here I see the word parameter, and that's an important word here. And parameter in a neural network model are made up of the numbers that control the output of each neuron. So that's not very clear. But parameters are the weights in a neural network. So I'll leave it at that. And then we also have neurons in a neural network. The weights are, I think you might have a picture of it here, but the weights are the edges that connect the neurons, and more or less. So here, you might ask an LLM, the capital of England is, and then you hope that it will give you an answer. And it might say London, or it might say the capital of England is London. It might give you various answers. And it says that this is all done on probability. So what does that mean? So when we're talking about predicting the word London, we're just looking for the most probable word. Now the question is, how do we measure probable? How do we get the probabilities? But anyway, skipping that, it's the most probable word given these 1, 2, 3, 4, 5 words in sequence. What's the most probable next word? So there are many. We have so many words in the English language, and the LLM will actually assign probabilities to all of them. So here it might say the capital of England is popcorn. So popcorn has some probability. It's not a zero probability, but it's hopefully will have a very, very low probability. But hopefully London will have a relatively high probability, maybe the highest probability of all the words in the English language. So across all the words, we assign probabilities to each of them, and then hopefully the one with that's London is the one with the highest probability. Now he uses the word token, not word, but so initially we were just talking about words. So in the study of neural networks and text inputs to neural networks, we would only be like predicting a word, but it turned out that for some reason it seems to work better when you break up certain words into maybe a couple pieces, which can't really hard to imagine why that would be better. I don't think I can imagine why it would be better, but it turns out that it's better. So what do I mean? You might break up the word, for example, speaking. You might have one is speak, and the next is ing. So the word speaking might actually be broken up into two parts, and so you'd only predict speak. So, or let's say it wouldn't happen with the word London, but let's just say it did happen with the word London. So you might break up the word London into Lond. Now I don't think that London would ever get broken up into two pieces, but let's just say it did. So Lond, so you'd have the capital of England is Lond, and then you'd predict, once you had the capital of England is Lond, then you'd do it again, and you'd hopefully get On next. So then you'd finally have the answer, the capital of England is London. So sometimes it just turns out that this works better for some reason. Maybe some people have some ideas about about why it works better. So if we really did want to break up this word London into two, like Lond and then, or whatever I said, Lond and then On, we would call each of them tokens. So Lond would be a token, and On would be another token. And actually, so they just use the word token to be a little more general than word, because sometimes it's not a word. So token can be a word, but it can also be like a part of a word. Or I guess it's even conceivable that it could sort of be, well, I don't think it ever happens, that it's more than one word. So it's usually either a word, I think we can say it's either a word or a part of a word. So we'll use the word token instead of word because of that. So they say, the atomic unit is the token. So that's like the smallest unit is the token, not actually the words. The token can be just a word, but it might be a part of a word. So actually they say sometimes it's even larger linguistic units. So I guess that happens sometimes. So there are different algorithms for splitting up or creating these tokens, and so that and some of them work better, some of them work better in certain circumstances, and so on. And I'm not sure if anybody can say clearly why these one algorithm works better than another, but we'll just leave it at that. And actually, OpenAI came up with something they called it the GPT 3.5 tokenizer. It's also called this, I guess. Uh, and if you had a phrase like "Good morning, dearest friend," it would break it up into 5 tokens. Now, how many words are there? One, two, three, four. But it would break it up into 5 tokens using this to mean a space character. So you'd have good, and then this would be a token. So this would be like the next prediction, and then or this sentence would be broken up into good, space morning, but it's space morning together, and then I guess DE turns out to be the way this so-called tokenizer splits up this phrase. So it actually space DE, and then I guess the IDs like I guess each token has like an ID, right? If we're going to have, so you might have 50,000 words in the English language, or more or less, whatever it is, and so each of the words in the English language is going to be or part, combinations of words or whatever, parts of words are going to be tokens, and they're going to have actually IDs. So these are just like an identifier for each of the tokens. So this one has the ID this, and this one has the ID this, and this one, dearest, has that, and friend, and so on. Okay, usually tokenizers are trained with the objective of having the most common words encoded in a single token. So that's good. At least the most common words. But actually, I mean, dearest is pretty common, I would think. But dearest wasn't encoded as a single word. So it's not always true. But he says usually the most common words are encoded into a single token. For example, the word morning is encoded as a single token and has this ID. And less common words, or words in other languages, require several tokens to encode them. For example, dearest. Why is that? That's not a... Well, I guess he's suggesting that's a less common word. So it's not a word from another language, but maybe it's a less common word. And so this one is encoded with 2 tokens, DE, or maybe it was space DE. Yeah. And then, so this one was 409, and this one was this number. So that's what he has here. And he's saying that tokens are usually only 4 characters. Okay. Okay, so this is just to give you an idea of how they actually split up words, and so that determines what we can predict. So you don't predict words, you predict tokens. So you don't in these LLMs, they predict the next token, not the next word. And so they might end up predicting, like we said, like this token. Okay, so this is just to give you an idea of what's going on. It's not something we necessarily... I mean, you can choose, if you happen to be training your own LLM, you can choose a tokenizer. There are various ones. So there's the one that he's talking about is called, what was it called? This one, or this one. But there are other tokenizers. Or you don't have to use a tokenizer. You can just use the words themselves as the tokens. Okay, so we see that there's some similarity between that task of word completion and what the LLM does. But one thing that we didn't say anything about was how are those probabilities assigned. So we're trying to predict the next word, and we have, say, 50,000 different words or 50,000 different tokens, and we want to predict the next one. So, and we said we were going to probably pick we will pick the one with the largest, greatest probability, but how do we assign probabilities to all the words? That's the magic, right? That's the question. And this is a neural network that does this, and it's a little more than just the typical neural network, because typical neural networks don't only deal with numeric data or numbers, and words are not numbers, so they had to come up with some way to make neural networks be able to work with numbers. And I remember a long time ago, thinking about how to do that and so on. But anyway, that's the problem. So the current way is the LLM, and um, that's really the LLM is actually it's a certain kind of neural network. It's called a transformer. So it's the transformer neural network architecture that that's generating the probabilities, actually. So here it goes into, it says, like, this transformer enables models to handle sequences of data. So it used to be that neural networks just would handle some input data, but if there was a sequence, like suppose you had data about stock market prices, you wanted to put them in, like, what happened 14 days ago, 13 days ago, 12 days ago, 11 days. So that's a sequence of days of data. And, the order is critical, right? I mean, if it was really high 14 days ago and then gradually got lower and lower, if you switch around the order of the data, that's going to mess up your prediction, right? If it was high and it was getting lower and lower, then you probably predict that the price was getting even lower. But if you could just move around the order of the prices day to day, you might end up predicting that the price is going to get higher. So the sequence is important in that kind of situation. Same thing with text data. The sequence is obviously important. You can't switch the order of words and get the same meaning. So they had to come up with something, because neural networks didn't recognize sequence at all. So they had to come up with some way to hold on to the sequence. And that's what we end up with the transformer. So a key word here is that it's a sequence of data, or sequence of words, sequence of prices, or something like that. Some sequence. That's what the problem that the transformer was kind of designed to handle. And then, what do we mean by the prompt? I think we know what we mean by the prompt when we go to ChatGPT, but that's the prompt means the sequence of data that we're feeding in as our data, and then we want to predict the next word. So that's the prompt. It's the sequence that we're feeding in to our neural network, to our transformer. And then there's, prompt engineering, means how to write prompts. And we might talk about that, but right now we're not going to go into that. Okay, so let's see what we have here. So they say that you need to train the LLM, you need to teach it how to make good predictions. And they say that that's usually called pre-training. So that's like the basic LLM is already been trained, and it's been trained on a large amount of data found on the internet, books, newspapers, code, video transcripts, and so forth, in a self-supervised fashion. So that means, basically, it means that it's a supervised fashion. Means that you have labeled data, but it's a little bit different because you take a sentence and you want to use that sentence for training. So what they do is they'll take out one word from the sentence, or perhaps the last word, but typically I think it's in pre-training. I think it's you just take out any word, and then given all of the words surrounding that word, like given the entire sentence except for that word, you try to predict what that one word is. And then you can call that labeled because you know what the real word is, because you just removed it, so you know what the real word is, and you can measure, therefore, how good you're doing, and you can do back propagation because of that. You can train the model because of that. So they say actually you could use a sentence and just use part of the sentence and predict the next word. So that's one way to take just a sentence that doesn't actually have a label, and then you can try and predict the next word. So you do have a label in that sense because you know what the correct next word is. Now this example seems not to be that case because he's pulling out a word from the middle. The capital of England is, and London. Okay, maybe he's saying, I don't know, that this is what you're predicting, but it's not clear what this is. It might even be a typo in this text, or rather in this PDF. And then, on the other hand, like I said, you can pull out a word and try and predict what it should be. So the blank of England. Oh yeah, I guess. Oh, I see. So they're saying, and capital. So this is the actual true answer, and this is what you're trying to predict. Okay, and I guess then the same thing happening here. So this is what you feed in, and this is what you're trying to predict. Okay. So honestly, I can remember when I was in about 2010 or 11, I started to collect internet data of various kinds, trying to. I thought, I can use it for, it's like data. And one thing back then was that there was no data. It was very hard to get data at that point. And it occurred to me that, the internet is just like this free source of data. So I started to download Twitter data. I started to scrape the web and so on to collect data, but it didn't occur to me. I couldn't figure out how you could have labels for this data. So, if you're doing machine learning, we called it data mining back then. If you're doing that, then you need labels. But I couldn't figure out how to turn the data that I had, and I had a lot of data, into labels. I used it for various things slightly different than this, and I really wanted to have labeled data, and I couldn't figure it out. But this seems kind of so trivial, but at that point, I spent a lot of time trying to figure out or thinking about how to get labels out of this. So this was a very big deal when someone came up with this idea for dealing with sentences and how to make it into labeled data. So next he says that even though you have this so-called pre-trained model, after you've done this for gigabytes of data, after you've done this for gigabytes of data and you're training the model with all these sentences that you've scraped off of the web, it doesn't do a great job of sort of talking to you or to answering your questions at all. It doesn't do a good job at all. So, you might think, well, why not? Because I put so much data into it, but it doesn't do it. So they give an example here. They say that you might get a good response by saying the capital of England is, and then you might get London, but not with the more natural, what is the capital of England? So, like you might get here, if you put in this prompt here, put in this prompt there, then you might get something like, what is the capital of Germany as the answer, because that might be the way the data occurred frequently in the scraped data that you had. So there might be a lot of questions. For example, what is the capital of England? What is the capital of France? What is the capital of Germany? And so on. So anyway, the thing is that you don't get the kind of answers that you want. So, so researchers had to figure out some way to push this even further, so that you could get the kind of answers that we would like to get. And obviously, it works now because you use it all the time, so you know it works. But it doesn't work just with the pre-trained model. So here they're saying that the next thing you could do is you could do what's called fine-tuning the LLM, or the pre-trained model, rather. Okay, so we saw that just the pre-trained model, although we can say it contains an incredible amount of information, but it doesn't really have the ability to deliver that information to us sort of in the way that we want. So, we want to be able to ask a question and get the answer to that question. So it's there, but it doesn't come out very easily. And you wouldn't know that it's there, except that they were able to design a way that it will give answers in the way we expect. And so then we can prove sort of that it's there, that the information is actually in the pre-trained model. So we can do what's called fine-tuning to achieve this, get it to answer properly. So there's one kind of fine-tuning actually is not exactly that, but rather to add specific types of data to the model. So we can do task-specific data sets. We can use task-specific data sets. So like this, what is the capital of England? So we're going to make this data set that has these kinds of questions and answers. Okay, so actually this will improve the type of responses we get. So what is the capital of England? Answer: the capital of England is London. So unlike the pre-training data sets, these are manually assembled, so they are by necessity much smaller, a much smaller data set. And then there's something called reinforcement learning, which is kind of a different process. Not kind of, it is a different process. And this is reinforcement learning with human feedback. So this is these manually assembled data sets are augmented with user feedback received on the output by the model. So we kind of get users to score the answers. So the capital of England is London, and that might be preferred by one user rather than London is the capital of England. So anyway, in any case, we get the user to score that, and that's where the HF, human feedback, comes from. So we might call it also instruction tuning. So here he points out that Claude or Anthropic might do things one way, and OpenAI might do them another way, and Grok might do them yet another way. So it's not uniform, what we're going to be talking about here, but here are some ideas about dialogue-tuned LLMs. Okay, so now he says that fine-tuned LLMs, that can mean various things, and it could mean instruction-tuned or dialogue-tuned, but it can also mean just like when a company takes their own proprietary data set and trains the LLM on that data. So that data would be not available to Anthropic, not available to OpenAI. And so if they want to use that data in an LLM, they have to train the LLM with that specialized data, and we can call that fine-tuning the LLM. It says technically also fine-tuning can also include instruction tuned, as we just discussed before, but usually it's reserved for the meaning of taking proprietary data and including that in the model. So then he says that when you do that, you might get a loss of generality. That is, they become less capable of answering queries on unrelated tasks. So, but sometimes that's certainly worthwhile. Now he says that when he talks about LLMs in his book from now on, he's going to mean instruction-tuned LLMs. So not just the pre-trained model. And for chat model, he's going to mean dialogue instructed LLMs. So that's when we teach it how to sort of respond in a human style dialogue. So he's going to call that a chat model. Okay, next he's going to talk about brief primer on prompting. So we'll take a look at that. Okay, so now he is shifting to saying the main task of the software engineer working with LLMs is not to train the LLM or even to fine-tune one, but rather to take an existing LLM and work out how to get it to accomplish the task you need for your application. So now we're shifting to the idea of using an LLM in a process. So not just chatting with it, although prompting, initially at least, is about chatting with the LLM. So he says that we have these LLMs, and they're released free of charge for others to build on. So he's talking about free ones and also OpenAI. So I'm not quite sure what he means by free of charge for OpenAI, but okay. So anyway, the idea is, how can we build on the LLM or build something on the LLM? So he calls it adapting an existing LLM for your task. And now he calls that prompt engineering, but I think that's called agentic AI. But let's see where he goes with this. So now he mentions LangChain, and that's part of an agentic framework. We're going to try and focus mostly on LangGraph and maybe some other frameworks, but LangGraph is part of LangChain, but it was developed after LangChain. But he says he wants to focus on prompting first. Okay, so now he says you can go to OpenAI, maybe this address, and you should be able to get a API key there, and they give you a certain amount for free, and that is a certain amount of usage for free. I'm not sure if he's going to be using the API key just yet, but he says you can also go to the OpenAI playground and test out some prompts. So that looks like this, and you can have what we're going to call a system message and the prompt message. So system message is like here, describe desired model behavior like tone, tool, usage, response. So you can say like, you should be a helpful agent or something, general commands like that, and it will read that for every time it gives you a response. And then the prompt message, and it's called the user here, and that is what you would typically type into the to ChatGPT or Claude. So here you can see you can choose the model that you want to use. So there's a bunch of them here. You can add in some variables and functions and so on. So he says you can choose the model of your choice. If you look down further down the panel, you'll see temperature under the model configuration title. Move the temperature toggle from the middle to the left until the number shows 0. Essentially, temperature controls the randomness of the LLM. The lower temperature means less random or more deterministic. Okay, so next he goes on to zero-shot prompting. So what that usually means is you don't provide any examples about what you want the answer to look like. So the first and most straightforward prompting technique consists of simply instructing the LLM to perform the desired task. So how old was the 30th president of the United States, blah, blah, blah. This is typically what you should try first, and you might get some answer. So he says something about the answer isn't quite right. I don't know what the answer actually was. So now he wants to explore, he says you have to iterate on prompts and responses to get a reliable system. The next section expands on how, so we discuss something called chain of thought. Now, chain of thought was initially prompt-based, so you would tell the LLM to behave in what's called a chain of thought way. So basically, that's like to think carefully about the problem and break it down into steps and so on. But later on, chain of thought became part of the LLM. They did fine-tuning to get the model to automatically do chain of thought even without you prompting it to do chain of thought. But initially, it had to do with the way you would prompt it. And I think, let's see. So this is one of the first papers that was written about chain of thought. There were some others that might have come before this. These people were, I don't know where they were. These people were at Google. But I think, well, anyway, so this is one of the first papers about chain of thought. And we could read it. Let's see what they say. We explore how generating a chain of thought, which is what? A series of intermediate reasoning steps, significantly improves the ability of large language models to perform complex reasoning. In particular, we show how such reasoning abilities emerge naturally in sufficiently large models by a simple method called chain of thought prompting. So where a few chain of thought demonstrations are provided as exemplars in the prompting. So as I said, this was prompting based, and so they're going to give some examples of what they mean by chain of thought prompting, by chain of thought reasoning, and they're going to give that in the prompt, and then the model sort of understands what is wanted and behaves accordingly, hopefully. So they say experiments on 3 large language models show that chain of thought prompting improves performance on a range of arithmetic, common sense, and symbolic reasoning tasks. The empirical gains can be striking. For instance, prompting PALM, I don't know what kind of model that is, 540 billion parameters with just 8 chain of thought exemplars or examples achieves state-of-the-art accuracy on the GSM-8K benchmark of math word problems. So I guess what they're saying is, well, I don't know what they're saying, but I mean, basically they're saying that it really improved the performance. Surpassing even fine-tuned GPT-3 with a verifier. A verifier probably means something that's built into the model that can verify whether, for example, a math answer is correct. So that could be like a Python problem that can do math, which is not too difficult with Python. So then they give us an example of standard prompting and chain of thought prompting. So here, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls did he have? Okay, so that's not too hard. The answer is 11. Is that right? 5 and yeah. The cafeteria has. So these are I guess just some question and answer. So standard prompting. The cafeteria has 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? So it ends up with 27, which is definitely not right, right? If you start with 23 and you use 20, then the new answer is not going to be anywhere near 27. So, okay, so it didn't work too well there, but if they give it the right kind of prompting instructions, examples, then it improves the performance. So let's see what the example is for chain of thought prompting. So here, instead of just the answer is 11, it gives some kind of reasoning. Roger started with 5 balls, 2 cans of 3 tennis balls. Each is 6 tennis balls. 5 plus 6 is 11. The answer is 11. So it gives the reasoning there. Then it gives this answer. Then it sort of follows the reasoning that was done up here, and it gets the right answer. And just having this one case where it gets it right is not proof at all, right? It's just one example. But presumably, this worked in many cases, and for many problems. And so this concept of chain of thought prompting was useful and productive. So actually the paper is quite short, and it probably just goes through primarily it just goes through and reports the results. So they came up with this idea, they tested it out, and they're just explaining what they did. Okay, so first of all, we have just a zero-shot prompting, and now we have chain of thought prompting. So a very useful iteration is to further instruct the model to take time to think. This technique has been found to increase performance on a variety of tasks. Curiously, a more recent paper suggests that this technique can also reduce LLM performance on tasks where thinking reduces human performance. That's interesting. So here's that paper that was in a little bit later in 2024, and then revised after that. Mind your step-by-step. Chain of thought can reduce performance on tasks where thinking makes humans worse. So when thinking makes humans worse, which I'm not sure when that happens, but it's conceivable that it could, then maybe chain of thought also makes the LLM worse. So there are probably some tasks where telling people what to do is not really useful, like if they're just doing something that's kind of intuitive, or trying to recognize some kind of pattern, probably words might get in the way. And apparently in some of those tasks, that can also happen when we sort of try to tell the LLM to follow a kind of reasoning pattern. Maybe we just didn't tell them the right reasoning pattern, though. But okay, so here we can see an example of chain of thought, but we already saw that, so we won't. We already saw some examples of chain of thought, so we won't go into that. So apparently here, maybe all they said was think thought step by step. Maybe that's the only change. So maybe even that can get it to make a difference, although I'm not sure if that's a result of the model having been trained to do that, or if even without that, this additional part, I was just saying, think step by step might make a significant difference. But here he says, actually, even though it did think by step, it still got the answer apparently wrong. Okay, so now we want to discuss another technique for improving the performance, and this is called retrieval augmented generation. Now, I wouldn't exactly call this prompt engineering, but you could call it prompt engineering, and you'll see why you can call it prompt engineering. So retrieval augmented generation, called RAG, R-A-G, consists of finding relevant pieces of text, also known as context, such as facts you'd find in an encyclopedia, and including that text in the prompt. So the RAG technique can, and in real applications should be combined with chain of thought, but for simplicity here, we'll use these techniques one at a time. So, okay, so what are they talking about? Well, so again, suppose you're a big company and you have a lot of proprietary documents, and they are documents that OpenAI doesn't have access to, hopefully. And so you want, so one thing you could do, and I mentioned it earlier, is you could fine tune on that documentation. They did say that sometimes that reduces performance in other areas. It might increase the performance on the information in the proprietary documents, but then maybe the LLM doesn't perform as well in places where it used to perform well. So that's one possible problem. But RAG is another way to deal with the same problem of this proprietary documentation, and that is basically you kind of treat the proprietary documents as sort of like a data set or a data storage or like an encyclopedia or something. And what you do is you take your prompt, which might ask questions about this proprietary documentation, and you sort of search through all of the documentation, the proprietary documentation, and you find the relevant, so-called relevant parts. Now, finding the relevant parts, that's not exactly just a simple task, because you might be finding maybe relevant parts don't even have the same words as your query. They're just sort of your query might describe things abstractly, and it doesn't specifically mention any of the important words that would match in the proprietary document. So it's not just word matching or anything like that. It's different. So that's a tricky aspect of this, and there's kind of an elegant solution to it. But anyway, the point is that you treat your proprietary documents as though like a kind of an encyclopedia, and you search through. And again, I said that's tricky how to search, but anyway, you search through, and you get the paragraphs or pages or whatever, let's say paragraphs, that are relevant to your query. And then once you have those, then the idea is basically you just take those paragraphs, and in addition to the query that you have, you're trying to query the LLM about your proprietary documents, but it doesn't even have those. The LLM doesn't even have that. But you take your query and you attach with it, you say something like, okay, my query is, tell me about the, how we do purchases of XXX or YYY. Tell me how we do purchases of that. And then you get paragraphs in your proprietary documentation that have to do with how to do that. And so you say, how do we, what do we do when we're trying to purchase XXX or whatever? And then you, in addition to that prompt, that very short prompt, you attach all of those paragraphs that are relevant, that are deemed relevant. And then you send the whole thing, let's say there were 10 paragraphs, plus your very short prompt. So you send the very short prompt plus the 10 paragraphs to the LLM. So now the LLM has all of that from your proprietary documentation, and it can try and answer the question. So in a sense, this is a prompting technique, right? But it's augmented by having access to the proprietary documents. Now, like I said, it's a little tricky how to find those, and that's a whole other subject which we may not cover, but we basically store those as what we call vectors, and we store them in what we call a vector database, and then we can, then once you do that, then this process of finding them becomes kind of a mathematical problem, and it's actually there's actually a nice solution to it. Now, when I say solution, I don't mean like a mathematical solution that has like a single answer. I just mean that it's it will get us a lot of the relevant information. So we kind of provide maybe it's called the context, and we provide the context, which is the all of those paragraphs, and then we still send our question, and apparently now it says we get a lot closer to the answer. It's still not right. I don't know what's going on here, but it's saying that LLMs aren't great at out-of-the-box math. Now, the LLMs that we use maybe prior, after the writing of this textbook or this book, are, they are actually pretty good at math for one reason or another. They might be using what we call tools, or they might just have gotten better at doing math somehow. But here, apparently, it still wasn't that good. But still, this illustrates the idea of RAG, or Retrieval Augmented Generation. Okay, so the next idea is what's called tool calling. So we want to take a look at this, and we'll take a look at that now. Okay, so we're talking about tool calling. So this is like, for example, a good example of this is that if you tried to use ChatGPT when it was first released at version 3.5, which I think was around the end of 2022, it would always tell you, I'm sorry, I can't find that information because it's beyond my cutoff point, meaning, the cutoff point might have been like the beginning of 2022 or something like that. So it didn't know anything about anything after that. And that's because the LLM has to be trained on a lot of data. It takes a long time and it costs a lot of money. So they don't just retrain it every day with the latest data. So they might only do it once every 6 months or once every year. So that means that it doesn't have typically the most current up-to-date data. So that was still it was an amazing machine. The LLM was an amazing machine, but it did have that problem. So then they decided to make web search available. So in other words, the LLM itself is just a neural network. It doesn't have web search in it. It's just a simple or not so simple neural network. It just simply doesn't have web search. It's like if you have a calculator, does that have web search? No, a lot of things don't have the ability to search the web. So, and an LLM didn't have the ability to search the web. So they wanted to provide that service to the users. So you can easily build a Python code to search the web. So here's some code to search the web. So we use requests and BS4, which is just sort of to clean things up, because the web, when you search a web page, it has all kinds of extra tokens in it, and you need something to clean it up once you grab it from the web. So we use this thing called requests, and it has something called get, requests.get, and you can put in a URL, and then you get the response, and then this beautiful soup cleans up the response, and then you just parse it, and that's it. And then if you want to use it, we created this function, search the web, so you just run that function, and you can search for this. So it's easy to build a Python program to search the web. I guess we could try this. Okay, so I tried it. I installed that stuff, and then I just ran this, and you get some web pages, I guess. Um, Wikipedia, what is machine learning, various. We only asked for to print out the first five, so we got out five results. Okay, and I guess it has the URL here and so on. So it's easy to do this to search the web. So this is some Python code which allows you to search the web. Okay, and then something else besides searching the web that we might like to do with an LLM. Basically, an LLM is not, particularly good at doing mathematics. Maybe it can do some math, but certainly wasn't built to do mathematics. And a Python program could do a much better job of doing math. So we might build, for example, a function to add two numbers or to multiply two numbers, or to we might have employ a function like the sine function or whatever. We might, we can build such functions in Python, and they're going to be more accurate than than typically what an LLM will do, because they specifically are set up to do math. But um, when an LLM does math, it's really just sort of probabilistically choosing the best answer from sort of maybe 50,000 or, well, many possible answers. Okay, so that's not really math. That when you probabilistically choose an answer, that's not what we think of as math. So maybe they'll get the answer right, but it's not really doing math. So LLMs don't really do math. So if we want to be careful, we can use one of the functions that we can build with Python to do math. Okay, so these are called tools. So the web search is a tool. It's a Python program, and the math functions that we could build are also called tools. So it would be nice if we could get the LLM not to try to do the math by itself, or give it and tell it, oh, by the way, we have these Python functions, and you can run them. Or actually, the way it works is you can send us a message, and we'll run them, and then return the answer to you, and you can sort of parse that answer and do what you want with it, but you don't have to do the actual math yourself. So it would be nice if we could do that. Same thing with the web search. Um, we'd like to tell the LLM, well, if you need extra information, you can call this, you can tell us, and we will run some Python program that searches the web and get that information that you want, and then we'll give it to you, and then you can deal with that. So it's sort of like what we were talking about with RAG before, where we would give some extra information, but in the prompt that we get by searching through the proprietary documents. We talked about that. So it's sort of like that. We're going to get some information by running our Python programs, either math calculations or web searches or whatever else. We can think of so many different possible so-called tools that we might be able to build and provide that access to the LLM. So once we do that, it's sort of like feeding that information as part of a prompt to the LLM. So it's a little bit like RAG in a way. So, we want to do this in a kind of organized way. So what we do is we when we first communicate with the LLM, we say, "Oh, listen, by the way, we have, these tools that we can run for you." So maybe you've built 100 tools that the LLM can use. So you say, "We have these tools," and we list them. We send part of the message that we send is we provide a list of the tools, and then just giving the name of the tool isn't necessarily going to tell the LLM exactly what it can do. So we want to be more clear than that. So we also provide a description of the tool, and and then what happens is the LLM um, will check the list of tools when it's answering a question, and it will check to see if, based on the descriptions, whether it thinks that the tool might do a better job than it will do. So maybe we have to write that in the prompt. So we might have to say something like, check the list of tools, and if you see something by way of their descriptions that seems like it might do a better job than you can do, then run that tool. Now, what does it mean to run that tool? It means send us a message to run the tool, because the LLM doesn't really have, it doesn't, it's just a neural network. It doesn't have the ability to run the tool. It can basically only answer questions, or basically only predict the next word. So that's not running a tool. But it can send us a message telling us to run the tool. So when we get the message, we'll be sort of looking out for whether uh, the LLM is just giving us an answer, or whether it's asking us to run a tool. And if it's asking us to run a tool, then that can trigger, um, like we can have an if statement, and that will trigger the uh, the running of that tool. And so, in our program, we'll run the tool that adds two numbers. Now, the LLM um, has to give us the arguments to the function that it wants us to call. So if it wants us to add two numbers, it has to provide us with the two numbers it wants to add. So, you might think, well, we just sent it the fact that we wanted to add 5 and 2. That's not what I'm saying exactly. I'm saying it might have to do a lot of different steps, and one of them is adding two numbers, and it realizes that it's not necessarily part of what we um, ask it to do. Like, we don't say add 5 and 2. I mean, we might say that, but it might be different than that. It might just, in the process of solving a problem, it might realize that it needs to add two numbers. And so when it gets to that, it might ask itself, well, do I have a tool for this, or is there a tool for this? And if it does know that there's a tool, so then it sends back a message, says, run this tool, and here are the parameters for that tool. Because the tools are basically functions, and so functions have parameters, and we need to know the parameters in order to run the function. Or we need to know the arguments. And then once we run that function, we get the answer, and we send back the answer. So this is kind of like, gets kind of messy, right? Because it has to send a message back to us, then we have to send we have to run the tool and then send the answer back to it, and we could be sending messages back and forth all day. So it's kind of messy, and this passing of messages is something that LangChain sort of organizes for us, so that we don't have to sort of write all the details of the program, the programs that have to pass the messages back and forth to the LLM. So LangChain, I mean, we could definitely write such a program ourselves, but you don't want to have to do it all the time. Like, maybe try it once, see how it works, see what it means to do it, but then maybe have LangChain, which sort of handles it in a more with a more abstraction a higher level of abstraction might just be easier to use. So that's the sort of purpose of LangChain. Okay, so let's read what they say here. The tool calling technique consists of prepending the prompt with a list of external functions. So we're going to tell it some functions that we have, um, that the LLM can make use of, along with descriptions of what each is good for. So we need a description and instructions on how to signal uh, in the output that it wants to use one or more of these functions. Okay, so we have to tell the LLM has to tell us, has to communicate with us that it wants us to use these functions. Finally, you, the developer of the application, so we're talking about building some application where we not just relying on an LLM, but we might have just a program, and in certain points in that program, we contact the LLM to sort of help us. So this, could be a sort of powerful tool that we could use in our programs. For example, LLMs can read natural language and basically understand it, whereas a program you have to basically code everything like with if-then statements, and if something doesn't match exactly, it will break. But with an LLM, that doesn't happen. It'll always give you an answer, at least. Might not be a good answer, but it won't just break, so to speak. Okay, so finally, you, the developer of the application, should parse the output um, from the LLM and call the appropriate functions. So here's an example of this. So you would provide it with a list of tools. So you'd say, okay, I've had calculator. So the calculator can accepts math expressions and returns the results. So you could build a little calculator in Python, and that would be a tool that you would have. And then you can have search this tool, and again you have a description. Here it is. This tool accepts search engine queries and returns the first search result. Okay, so you tell it that you also have a search engine, and then you give some more instructions down here. If you want to use tools to arrive at the answer, output the list of tools, and I guess that means the list of tools you want to use, and the inputs in CSV format uh, with this header, tool input, like that. Okay, so here now we have a question. How old was the 30th president of the United States when his wife's mother died? So that's kind of a complicated question, by the way. That was the question from earlier, I guess, where we couldn't really read what was in there. How old was the 30th president of the United States so first thing you have to do is figure out who the 30th president was. Then you have to figure out who its wife was. Then you have to figure out who its wife's mother was. Then you have to figure out when she died. And then you have to figure out when the president was born. And then you can do this number minus that number to find out how old the president was at this point in time. So it's pretty complicated. It's a pretty complicated question, actually. Okay, so might be what you feed in, and this is the output you might get. So we told it to write tool and input, so it does. And then it lists the tool that it used and the input to the calculator. So, we said we have to figure out when the wife's mother died. So the wife's mother died, I guess, in this year, and this is when the president was born. So this is the calculation we want. So we would sort of indicate this would be a message that it would send back to us. It would say, do the calculator and do this, use the calculator tool, and these are the arguments, or this is the calculation to do. Typically, we would say these are the arguments, but here it's not what he's doing exactly, but that's not exactly how we do it in the typical standardized way. Okay, but this is intuitive. And then search, and you put this in the question. So, so here he says, while the LLM correctly followed the output format instructions, so it did do this, the tools and input selected aren't the most appropriate for this question. I'm not quite sure what he means by that, but anyway, this gets at one of the most important things to keep in mind when prompting LLMs. Each prompting technique, and we've talked about several different so-called prompting techniques like zero shot, and I don't know if we mentioned one shot, but that would be where you put in one example. And we also talked about tools, and there was something, retrieval augmented generation, and chain of thought. So they're saying it might be better if we can combine some of these prompting techniques. For instance, here we could improve on this by combining tool calling, chain of thought, and RAG into a prompt that uses all three. And then he says, let's see what that would look like. So maybe this comes from RAG, and this comes from RAG, and this comes from RAG, and this comes from RAG. And then tools, we have a tool, a calculator. And then we say this, if you want to use tools to arrive at the answer, output the list of tools and the inputs in CSV format, and with this header. And then we have the chain of thought part of the prompt, think step by step, and then we have the question. And so here he says that we actually will finally get the right answer, which is 50. So the answer is 57. Okay, let's go to few shot prompting. So you can have a zero shot, we already discussed that, where you don't provide any example. And then you can have, I guess, a single shot or few shots. So this consists of providing the LLM with examples of other questions and correct answers. And this enables the LLM to learn how to perform a new task without going through additional training or fine-tuning. So it's, I guess, a kind of a shortcut to fine-tuning or additional training. When compared to fine-tuning, few-shot prompting is more flexible. You can do it on the fly at query time, but less powerful, and you might achieve better performance with fine-tuning. That said, you should usually always try few-shot prompting before fine-tuning. So here he talks about static few-shot prompting, which we just assemble a predetermined list of small number of examples, or you can use what he calls dynamic few-shot prompting, which is you can have kind of like a data set of many examples, and then you can use what's called a similarity measure, which hopefully we'll talk about later. But it's just a way to decide which are the, so, maybe one similarity measure, a very simple one, would be just to look for for example, in this case, the word, you take the example that has the most, the greatest number of words that intersect with your particular prompt. So, so that would be, then you could call it the element in the data set the most similar to your prompt, because it had the words that are the greatest number of words sort of intersecting with the words in your prompt. So that's one way to do similarity. That's an example of how we could judge whether things are similar or not. But there are other ways as well. So we can talk about different ways to judge or different ways to measure the similarity, for example, of the prompt to the example. And so here you'd have a lot of examples, and then in it like a data set, and then you take your prompt and you go through the entire data set and measure how similar your prompt is to each of the elements or each of the elements in the data set, and choose the one or the ones that are most similar. So you could do that as well, to obtain few shot prompting. Okay, next is LangChain and why it's important. So LangChain was a person who developed it. I think he made his first GitHub entry in 2022. I forget his name. I think his name was Harrison or something like that. You can look it up. And so, as I said before, you don't need to use LangChain, but it just makes things easier. You could program everything by hand, but the idea of LangChain is to abstract away some of the details so you don't have to do them every time. So LangChain was one of the earliest open source libraries to provide LLM and prompting building blocks and the tooling to reliably combine them into larger applications. So he foresaw the need to write applications that used LLMs, or maybe he didn't foresee it. Other people might have come up with the idea earlier, but he recognized it as an important task and something worth building a framework around. So as of the writing of this book, which was about sometime probably late 2024, when the book was started to be written, LangChain has amassed 28 million monthly downloads and 99,000 GitHub stars, and the largest developer community in generative AI. It has enabled software engineers who don't have an ML background to utilize the power of LLMs to build a variety of apps ranging from AI chatbots to AI agents that can reason and take action responsibly. And also, I think we can say that he developed a kind of pattern or a structure that other frameworks use. So it's kind of like learning a language. So once you learn one language, then learning other languages is easier than learning your first new language. And same thing here. Once you learn LangChain, then learning the other frameworks becomes a lot easier. And also, why does he say to build an AI chatbot? So why do we have to build an AI chatbot? I mean, isn't an LLM already an AI chatbot? So I was confused about that at first, because an LLM is not, I mean, we think of ChatGPT as being an LLM. We sort of use them synonymously, but that's not quite right. Of course, ChatGPT has an LLM at its root, but on top of that, they've built a lot of structure, and in particular, they built a chatbot on top of that. So what does that mean? Well, it can mean can be something very simple, or it could mean something more elaborate. But basically, it's let's call it a nice way or an easy way to interface with the LLM. So it's kind of the interface to the LLM. And what we'll learn later is that, for example, ChatGPT remembers the conversation that you've had as you have a conversation, but that's not native to just an LLM, as we'll discuss later. So anyway, there's a difference between the LLM, which is at the heart of ChatGPT, and the chatbot, which is sort of a more elaborate structure that makes it convenient and easy for us to use or access the LLM. Okay, so LangChain builds on the ideas that we talked about, the prompting techniques, and LangChain makes it easier to put these prompting techniques all together. So we can say LangChain provides a simple abstraction for each major prompting technique. And by abstraction we mean Python and JavaScript functions and classes that encapsulate the ideas of those techniques in easy-to-use wrappers. And they're designed to work well together and combine into a larger LLM application. And basically the code that you write with LangChain, if you can basically use the same code whether you're working with OpenAI or you want to switch to Anthropic or Google or open source models like Llama or Gemma. So there might be a few changes that you have to make, but basically most of the structure will remain the same. And as we'll see later, we get the prompt template abstractions. So these enable you to reuse prompts more than once, and sometimes you'll want to have a prompt that has some fixed text, but also some placeholders that you can modify. So you might say, I want to, you might say, you are an expert in the field of, and then the placeholder will be there, and you can put in any kind of any field that you want there. And LangChain prompts can also be stored in the LangChain hub if you want to share it with your teammates. And then LangChain also contains many integrations with third-party services like Google Sheets, Wolfram Alpha, Zapier, and many, many others. And they're exposed basically the same way that we make tools available. And we can call them like we would call a tool. And we'll see how we do that. And RAG is still very popular now. I had thought that it might become less popular, but it's not become less popular. It's sort of become the go-to standard for sort of magnifying the domain of the LLM. And we talked about how what RAG does. You have a bunch of proprietary data, for example, and you want to search through it. And I'm not talking about fine-tuning. I'm talking about RAG, where you want to search through the proprietary data and then only pull out the relevant paragraphs and then embed those in your prompt along with your whatever your regular prompt is, whatever your query is. So you're feeding the LLM sort of the information, and it can use that information to answer the question. And we use the word embedding to talk about how each, in this case, paragraph would be stored in the database. And the database has a different form than a typical database. And it's called a vector store or a vector database. And we'll talk about that later. But basically, we represent sentences or paragraphs. In the case I was describing, it was paragraphs with vectors. So a vector is just like a list of numbers, and that list can be long or short. So it could be a vector with just 2 numbers in it, a list of just 2 numbers, or 3 numbers, or 10 numbers, or 50 numbers, or 500 numbers, or 5,000 numbers. So, but we can use these vectors to represent each sentence, or in our case, each paragraph. So this is a technique that's been developed over about 40 years, and it's called a vector space representation of language, and it's very powerful, and and they're usually called embeddings now. These representations, these vectors, and there are many different ways to do that, and so we can say there are many different embedding models. And anyway, so LangChain gives us integrations with these. There are commercial and there are non-commercial vector databases or vector stores. They're also called vector stores or vector databases, and so we can connect with these easily with LangChain. And there's also something called a vector index, which is just like a regular database, like MySQL or even Oracle or something like that. And then they've gotten on the bandwagon, and they're including this sort of vector storing capabilities within their regular database. So those are called vector indexes. So we're talking about what is LangChain and why it's important. And it's also important for doing chain of thought reasoning. And so LangChain provides what we'll call agent abstractions. We're going to talk about agents that combine chain of thought reasoning and tool calling. So we saw what chain of thought reasoning was. So the simplest way is just to tell the LLM to reason step by step, but there are other ways to do it as well. But anyway, that's called chain of thought reasoning. And we also talked about tool calling. And actually, it's not a bad idea to combine these two. So you can have it reason step by step, and maybe at each step, it might consider whether it needs a tool. And we talked about the fact that we could have lots of different kinds of tools, and we gave two examples. One was web search, and the other was like a calculator, but we could have many, many other kinds of tools. In fact, we just saw above that we can consider like a Google Sheet like a kind of a tool, and Wolfram Alpha, which is like used for mathematics, more advanced mathematics, and Zapier has many, many uses. So we can combine chain of thought with tool calling, and this was first popularized in the React paper. So what the React paper does is we reason about the steps to take, and then as we take the steps, we can translate those steps into external tool calls sometimes, and then we can receive the output of those tool calls. That's called the observation typically, and then we can repeat, go back and reason about the next step to take, and then maybe we need to call another tool or more tools, and then check the output and incorporate that and continue until the task is accomplished. And here we're really putting faith in the LLM to know what tool to call and to do some real reasoning as well. Now, the next thing is the idea of memory for a chatbot, and this is typically very surprising when people hear this. It was certainly very surprising for me, and that was, somehow, well, if you just take a chatbot, if you just take an LLM and you ask, and you can easily implement this in code. For example, you can do this in Colab, something as simple as Colabs, and you can establish a connection with an LLM, and then you can start to talk to it. And the thing is, though, if you do it this way, so this is kind of a manual way of doing it, And if you do this and you say something like, hello, my name is Joe Smith, and it'll say, hello, Joe Smith, very nice to meet you. And then if you ask it the next question, you say, what's my name? It'll say, I'm sorry, I don't have information about who you are, or something like that. In other words, it doesn't remember anything from the previous chat. So that sounds very surprising, but if you remember that this is just a neural network and you're feeding in a prompt and it's giving you an answer, so you feed it in a prompt and you say, hello, my name is Joe Smith, and then it gives you an answer. But then you feed it in another prompt, it doesn't remember the last answer. It's just a neural network. So it doesn't remember anything about what other data you fed into it during inference, when you're running it. So that sounds very strange, but that's the way it is. It sounds strange because that's certainly not our experience when we use ChatGPT or Anthropic or whatever. Of course, it remembers, long conversations, but that has to be handled outside of the neural network, outside of the LLM. So we have to implement that somehow, and it's quite surprising, actually, how it's implemented. So what happens is, so we feed it in a question, like, hello, my name is Joe Smith, how are you? So that's our question, and then it gives some response like, hello, Joe, or nice to meet you. And then we take that response, and then I think we actually take the question and the response, but at least the response, but I think we take both. And then when we go to ask the next question, we don't just ask the next question, which would be, for example, I said, what's my name? We don't just ask that. We say, we prepend that with, or we add in the previous conversation that we've had. So we add in the fact that I already said, hello, my name is Joe Smith, how are you? And then the LLM responded, hello, Joe Smith, nice to meet you. And then, what's my name? So we feed it all that information. And then if we ask another question, or we continue another round of this conversation, or another turn of this conversation, we add the entire history of the conversation. So that sounds almost preposterous, but that's exactly what happens when we are chatting with the LLM. So that's why we run out of space in a long conversation. What's happening is we're feeding this in this. We've had a long conversation now. And then we ask another question. We're attaching the entire conversation to that last question and feeding all of that in to the LLM. Well, that's you're going to eventually run out of space or run out of context in the LLM, and it's not going to work anymore. So that's actually what's happening. So that's why you get, sorry, we have to end this conversation. The conversation is too long now, but it's not like it's too long in the past, sort of. It's because you're feeding the entire previous conversation into the LLM when you ask the next question. But anyway, that's called the memory. When you feed in all your previous conversation, that's called the memory of the chatbot. So we have to manually do that. But of course, with something like LangChain, hopefully, they can sort of handle that much more easily. But otherwise, you'd literally have to handle this yourself. So basically, you'd have to have like a conversation history, which would be like a list, and you just keep appending the new the latest turn in the conversation to that list, and then you'd feed that list back to the LLM in your next question. So again, that sounds crazy, but that's literally what happens. Now, there are ways that they try to manage the length of the conversation. For example, they might try to summarize parts of it, maybe summarize the beginning or summarize the middle, and that would help to reduce the size of the conversation that you have to keep feeding into it. But those are sort of tricks that they can use to manage the conversation, But still, they have to do something like that. Otherwise, there would be no memory. Okay, and then we may also talk about something called LangSmith, and that's a platform to help you debug and test and deploy and monitor your AI workflows. And also, we're definitely going to work with LangGraph, which makes it is a very good extension to LangChain. Okay, to summarize what we've said so far, we've had a refresher on what makes LLMs tick and why exactly that gives you this kind of building or thing building superpower, and having very large machine learning models and the possibility of using them in other applications, and the fact that they can output answers in conversational English or some other language. And so we hopefully by the end of this course we'll see just how powerful this can be. So first we'll start with building an AI chatbot. Then we'll give it access to some documents that's like proprietary documentation, for example, so that it extends the knowledge from just being a generic chatbot to having specialized information. This is important for companies. And then we'll build in the memory that we talked about that's so critical. And then we'll talk about how we can use chain of thought and tool calling techniques to give the chatbot the ability to plan and act on those plans iteratively. So that will enable it to work towards more complicated requests, such as writing a research report about a subject of our choice. And then finally at the end we'll learn how to deploy the chatbot to production, and we'll discuss what you need to consider before and after deploying it to production, like latency and reliability and security. And we'll learn how to monitor the chatbot in production to continue to improve it as it's used.